All right, good. Okay, so we've added our lone pairs on the oxygen and the formal charge on the nitrogen. Now, when we try to draw resonance structure, the first thing that I would do is look at where the electron wants to go. Remember that electron wants to go where there is a lack of electrons. So in this case, nitrogen is positively charged, so it wants to receive electrons. And whenever we draw resonance structure, I always tell my students there's two ways that you can do this. Either by starting with pi electrons and sending the pi electrons towards an atom or a bond. This is option one. Or you can also start by electron pairs, and you can send the electron pairs to a bond. So in this case, we want to bring the electron to the nitrogen that is positively charged, and we have a double bond here. So what we're going to do is we're going to take those electrons from the pi bond and bring it to the nitrogen. So if we draw this first resonance structure, it gives us something like this. So we draw the rest the same way, we did not change it. Now we have those two electrons on the nitrogen, which now makes it neutral, and the carbon here lost one electron, therefore we give it a positive charge. All right, now you can do the same thing with the second molecule, where you're trying to bring electron to the positive charge on the carbon. And now, as you can see, we have oxygen next to it. So the two lone pairs on the oxygen will give the electrons and bring it into that bond to make a pi bond. So this is this example here. So if we draw that structure, right, one of the lone pairs still remains on the oxygen, and now this oxygen will have the positive charge. And finally, we can do the same thing again. We want to stabilize that positive charge. We have another doublet here on this other oxygen, so we can push the arrows this way. Remember that you cannot form 5 bonds on a carbon, so if we push this first arrow, we have to push a second arrow because we cannot have 5 bonds on carbon. So if we draw the product of this, it will be the following. Now, that terminates the first part of the question, which is to draw the resonance structure. Now, a bit more tricky is determine which is major and which is minor. So there's 4 rules to determine this. And in priority, what they are is the following. So first, you want to look at the number of incomplete octet. Second, you want to look at the number of charges. Third, you want to look at the position of the charge. This is true when you have one charge in your resonance structure. And fourth, you want to look at the separation of the charges. This is when you have 2 charges. So let's look at all of our molecules here and look at priority number 1 is the number of incomplete octet. So let's look at the first molecule. All of the octets are complete. The nitrogen here, even though it's positively charged, it has 8 electrons around it. So here we'll say the octet are fine. If we look at the second structure, we can see that this carbon here only has 6 electrons around it, and it is positively charged. So here we are missing, we have 1 incomplete octet. On this structure here, the third one, we have a full octet again. You can count for yourself. And same thing for this last structure here. So this tells us that this compound here, the second one, is the minor. The least stable, yes. All right, so that's priority number one. So it's the first thing that you should be looking at. Then 2 is the number of charges. In this case, all of the structures that we drew all have 1 charge, so we can't use this priority rule. Then we go to rule number 3, which is the position of the charge. Here we have 1 charge, so we're going to be following this rule. If you have 2 charges, you look at the separation of the charges, but we don't have that today, so we can ignore that. So the position of the charge. So if we look here, we have the positive charge on the nitrogen. Here we have the positive charge on the oxygen. So remember that we want to put a negative charge on electronegative atom. And we want to put positive charge on less electronegative atom. So in this case, we know that on the periodic table, oxygen is to the right to the nitrogen, so oxygen is more electronegative, nitrogen is less electronegative. Therefore, we want the positive charge on the nitrogen. It's going to be more stable. So that's why this compound here is major, because the positive charge is on the nitrogen. And finally, these 3 are actually the same structure because it is symmetrical. So this one gets number 3 because gets number 2 and 3 because the positive charge here is on the oxygen. All right, so this is how you answer this question step by step. Okay. So please mute yourself if you're not already.
I'll just add, this octet rule. I'm sure a lot of people know this, so I'm not really telling any tales out of school, but you count the lone pairs of electrons as 2 each, obviously, and each bond coming out of that atom is also counted as 2 electrons. So you see the nitrogen has 4 bonds, 2 sigma bonds, and a pi bond, which is like 2 lines. So each line represents 2 electrons. So you can count that as 2 electrons.
Yeah, you have 2 here, 2 here, 2 here. That's why you have a full octet.
Oh.
All right.
So
Can we mute these people?
oh boy.
Mute all here.
Ready to go. Ready to go.
All right. All right. So should we go to the next part? So we're going to be quickly talking about our link me. We stop sharing that. I think I have to do it on my computer. Okay.
So yeah, do you want to start? We could, we just set up this link me, which I don't know if I wasn't familiar with it before starting this, but it's kind of a convenient way to post links to all of our registration sheets, among other things. So if you visit the link that's posted in the in the group chat or scan the QR code, you'll be taken to our link me. From there, you can go to our YouTube, TikTok, Instagram, and whatever, Facebook. But we got our promo video here, and then if you scroll down, there's a little bio, and each of these is a link to our tutoring sessions. So this is today where we're at right now. In the future, we're going to post the Zoom links for our free sessions. So before every exam, we'll have like one free session like this, just to kind of let you guys get to know us a bit. You can add your contact information here too if you want, but more importantly, when you're registering for our group sessions, it'll take you to a Google Doc similar to the one you used today to sign up. So, we can just, let's say for the Zoom session we have next Wednesday before this exam, you can click here and it'll take you directly to the Google Doc. Some information, and then basically the same sign up information that you had before, with information to e-transfer. So it's like I said, it's just a very convenient way. We'll be updating this with the new sign up sheets for every exam and every session we have before every exam. So these sign up sheets will be constantly changing. But yeah, if you want to check that out, go for it.
Yeah, can you stop sharing for a sec?
Yep.
Just there. Yeah, and just so you know, the style of the sessions are really similar to what we're going to do today, where we're going to be presenting the concepts, kind of recapping the important concept, and we're going to do one example together to make sure everyone is on the same page. And then we'll have a series of other problem sets that are same as the midterm that you guys, similar to the ones that you will have on your midterm. And everyone's going to have a chance to ask questions. We can do multiple examples on one topic to make sure that you're all good for your midterm. And yeah, I think that's good. And just to mention, the way it works is that we prepare mock exams based on the midterm that you provide us, that your prof provided you with. So let's say you have the class with Elna Chef, then you would send us the midterm that she provided you, and then we would make a new mock exam based on her question. So when you show up to our group sessions, it will be really tailored to your class, and we'll be able to answer your questions, obviously, which is something that we're not going to be doing today. So that's different to the group session.
Yeah, due to time constraints today, and yeah, I can't answer questions, but the Zoom, the paid Zoom session will be way more interactive than this. And the in-person sessions are, we have a room booked at the Ottawa Public Library, which is just a 10-minute walk from campus. It's on Metcalf there. So we'll have a 3-hour block to really go over these questions and dig into them more thoroughly.
Yeah. Okay. So with that, I will start sharing my screen again, and we're going to go over the second question. Yeah, if you're interested in the session, we have added a QR code on our group chat on the Zoom. So you can just scan that code. It will bring you directly to our link me, and then you can register to the session.
Or also click the link. That'll take you to the same spot.
Yeah, you can click the link as well. Okay, let's jump into question 2, acid-base reaction. I know this is a problematic kind of concept for many of you, but I'm going to try to break it down today. Okay. All right, so this is one of the questions that I found on one of the midterm 2. So the question is, you have this molecule here, and it is asking what's the expected major species, I don't know how to pronounce that word in English, speciation, thank you, of this molecule at pH 5. So here it gives you 5 different options. So you have to figure out which one will be present majorly at pH 5. So for these questions, what I want you to do is use the pKa table that would be provided on your midterm. So let me redraw the structure here. Okay, so step 1 here is to determine the pKa. Of each of these functional groups, all right? So let's start with the phenol here. So what I want you to do is look at your pKa table and try to spot phenol in there. So Here I can highlight it. We have a phenol with the OH here that is highlighted. That's the pKa of that OH bond. Don't get mistaken with terbutanol, for example, or any alcohol, because the pKa here will be much higher. So phenol here is around 10. So I'm going to write pKa around 10. All right, so if we start with phenol, we have that. Now if we look at the amine here. So look at your pKa table. You're trying to find amine. Here it is. The pKa of that NH bond is 38. So I'm going to write pKa around 38. And finally, we have thiol at the end there. And here it is. Here is butane thiol. So it's pretty similar. It's an alkyl thiol, which is what we want. We have an alkyl group here. So we're going to write here, pKa is around 10.5. All right. Now to determine which will be the major species. So the way I like to teach this is with a pH range. So if I draw here a pH range, if we start with our alcohol that we said has a pKa of 10, what this means is that at pH 10, so here the pH is equal to the pKa 10. What this means is that you will have half in solution, half of it will be as the OH and half of it will be as the O minus. All right. Now, when you do these questions, I want you to write all these structures. This OH, so the structure that is in the question, I want you to remove one hydrogen to make the O minus. And I also want you to draw the structure when you add a nitrogen. So you would form the OH2 plus. Now I want you to go back to your pKa table and try to find H2O plus. And if I look at the table, yeah, sorry, H3O plus. So what? No, it's H2O plus because it has the C, the link. Yeah, this is correct. H2O plus. So for example, you have this. So we can say that the pKa here is around minus 2.2. So this means that at pH minus 2.2, which is the same as the pKa, at this pH, you will have 50% of the OH2 plus and 50% of the OH. This is what the pKa means. So now the question asks you at pH 5. So now I want you to go in your pH range and I want you to locate pH 5. So it's going to be between minus 2.2 and 10. So this means that the major species will be where you will just have the OH. All right. So this is one part of the question. Now we're going to do the same thing with the other three molecules, the other three functional groups. So let's do now the NH2. So again, I'm going to draw my pH range. I'm going to simplify the structure. So again, at pH 38, which is the same as the pKa of the amine. At pH 38, you will have a mixture of these two species that will be 50-50. Again, I want you to draw all three possible structures. So if I draw the ammonium now, I want you to go to your pKa table, spot the ammonium. I'm going to put it in pink here. Here we go, the ammonium. The pKa is 10.6. So you put 10.6. So at this pH, you will have 50-50 of the ammonium and of the free amine. Now, the question asks for pH 5. So again, pH 5 would be around here. So you look at which molecule is in this bracket. It's the ammonium. And so therefore, the correct answer for this functional group is NH3+. Because it has a pKa of around 10. All right, finally, we're going to be doing the thiol. So same exercise, we have the pH range. We know that we said that the pKa of the thiol is 10.5. So that means that at a pH of 10.5, both of these species will be present in 50-50 ratio in a reaction or in a mixture. Again, we draw the protonated thiol. So here, the pKa is around of this thiol here, or protonated thiol salt is around -2. And so again, the questions ask for pH 5. And so we look at which species is at pH 5. It's in this bracket, so we know that it's going to be the thiol. So this is how you answer this question, and we can tell that the correct answer would be E. All right. So that is our acid-base question directly taken from a past midterm. I will stop sharing.
Okay, now I will share my screen and do a mechanism question with arrow pushing, which can be daunting to some for sure. 1 second here. Just want to make sure that I can see it. There we go. Okay.
I'll see the microphone.
Okay. I'm hoping that everyone can hear me okay. So I'll put it in reading view and I hope the animations work. Okay, so this question again taken from a midterm in the mid 2010s or the late 2010s is just a mechanistic question. So the verbatim, the question is draw the mechanism of the acid catalyzed reaction of 4-phenyl butane 2-one and methylamine using arrow pushing. Include lone pairs and formal charges for all products and intermediates. Nope, I misspelled intermediates there, but anyway. So hopefully that with your IUPAC nomenclature, we can deduce that this compound here is 4-phenyl butane 2-one. And this is methylamine. Methanol here is just a solvent, and HA is a general formula for an acid. Oftentimes in this reaction, fun fact, acetic acid is used as the acid catalyst, but that's neither here nor there. I just thought I'd add that bit of trivia. So how do we start? Much like Alice was just explaining in the first question, we're going to add lone pairs to all our atoms that have lone pairs, in this case, the nitrogen and the oxygen of the carbonyl. So step one is the nucleophilic addition to the carbonyl. Some of you may have seen this already, some not. You will soon if you haven't seen it yet. But when you see a carbonyl, should automatically be thinking that there's a partial positive charge at the carbon and a partial negative charge at the oxygen. This has a pretty strong dipole with electron density localized around the oxygen. And in this case, the nucleophile is the nitrogen here on methylamine with its lone pair. And as the title would suggest, the nucleophile adds to the electrophile. The electrophile in this case is the partially positively charged carbon. Remember, positive things like electrons, they're electrophilic. And negative things like electrons, like positive charges, they're nucleophilic. So the first thing that happens here is the electrons attack the carbonyl carbon. And when a bond is made, another bond is generally broken. In this case, the weakest bond is the pi bond between the oxygen and the carbon in the carbonyl functional group. And just to throw back to what Alice was saying, a carbon never has 5 bonds around it. There's no such thing as pentavalent carbon. So if you're ever drawing structures with 5 bonds around a carbon, you got to rethink your strategy because that's definitely not the right answer. So anyhow, the lone pair attacks, electron density is pushed up and another lone pair is delocalized over the oxygen atom. This is an equilibrium process, and this results in a formal negative charge on the oxygen and a formal positive charge on the nitrogen. This is the tetrahedral intermediate that I'm assuming some of you have seen up to this point. So remember I mentioned there's solvent floating around the system. In this case, it's methanol. And in this case, the solvent can act as both acid and a base. So when it's acting as a base, the lone pairs on the solvent oxygen deprotonate the nitrogen, and these electrons go back into the nitrogen atom center and quench this positive charge. And in the other case, it acts as an acid whereby the lone pair of the oxygen picks up a proton to quench this negative charge, and then the electron density is delocalized over the methoxy anion. So what we get is another equilibrium process which favors the product side here to form an amino alcohol. Okay. Now this amino alcohol can undergo acid catalyzed dehydration. So upon addition of some generic acid, what happens here is the lone pairs on the oxygen again pick up this proton, and the electron density is delocalized over the conjugate base, and we lose A minus and end up with this oxonium cation. So this is like the CH2 plus or OH2 plus, sorry, that Alice was talking about earlier in her acid base lesson. Remember, we have this conjugate base floating around now. I didn't draw the lone pair here, but it does have a lone pair. And I was told that you always draw arrows coming from lone pairs. Never draw the arrow coming from the negative charge because you'll lose marks that way. So in this case, the lone pair will deprotonate the nitrogen again. The electrons will be pushed to form a double bond between this nitrogen and the carbon, and water, neutral water, is a very good leaving group, so that will leave. Now, once this process occurs, it's no longer reversible, and this is your final reaction product. Water gets kicked off, and you form this species here, which is known as an imine. Carbon double bonded to a nitrogen is an imine, I-M-I-N-E. So this would be your final answer for the product of that reaction. And just as an extra maybe bonus, if we hit this compound with a reducing agent such as sodium borohydride, I'm not going to draw the mechanism here, we end up getting just an amine. This whole process is referred to as a reductive amination, which is a very common synthetic step that we use in the lab quite often. So yeah, starts with a nucleophilic attack, then dehydration, and then finally a reduction to make the amine, reductive amination. But in the context of this question, the final product would be this. That's the answer.
There's a few questions in the chat that I'm going to answer, but
Yeah, we have like about 20 minutes left, so we might be able to get to a couple of questions.
but
Should I stop sharing?